hi everybody. First of all, let me start by thanking the organizers of today for having me. It's been a pleasure to be in Israel for the first time, and I've really enjoyed the talks and the welcome so far. So my talk will be about understanding your customers. Very easy, very simple, and hopefully very interesting to all of you as well. So a little bit about me. I've already been introduced. I come from the University of Leuven. I have been working as a doctoral researcher there, currently working there as a postdoctoral researcher, and soon to be an associate professor at the department. Now, traditionally, my research is more oriented in the business process domain, using techniques stemming from process mining, but we have been working on many data mining related projects as well. Also interesting to know is that I co-chair data mining apps. Nowadays, in Belgium, most of our funding, at least, especially in the field of data mining, comes from the corporate sector. It doesn't come from the government anymore. So many of our projects are, by definition, very applicable and in cooperation with companies there, as well as this project I'm going to talk about today. So this project was joint research together with Alex Barbases and Jan van Tiene at our department. And was for Ticketmatic. Now I'm going to take 1 minute to explain what Ticketmatic is. It's a company in Belgium which provides middleware services to venue and event organizers. So imagine something like, I guess some of you must have heard about Tomorrowland, for instance, in Belgium, or other concerts. Well, they use Ticketmatic to provide them with the software to sign up customers, to sell tickets, and also to do the after-sale analysis of this, which is, of course, also very interesting to their partners. So they want to know, after they sell tickets for a certain concert or opera, whatever fancies your boat, how many customers came by, in which age groups did they belong to, in which social demographic groups did they belong to, how can we do better next time when we want to sell them return tickets, and so on and so on. So they want to provide that sort of analytics to their clients as well. So they came to us with a project and they said, well, we have some analytics going on, but it's mostly like very traditional standard stuff BI, right? I mean, we measure some things, we have some metrics going on, we have dashboards, but that's it. So how can we reach the next step and provide some deeper analytics here? So that's what we did. And to do so, first of all, we presented them the case of, are you willing to do classification? Are you willing to do regression? Are you willing to do supervised analytics? Because we can predict for you, if you set up a certain concert, how many sales you will have. We have the data to do so. They have millions of customers in Belgium and the Netherlands, so we have the data to do so. But they said, yeah, you know, supervised analysis, that's all nice, but you should also understand our customers. They really like to delve into the data themselves, and they really like to explore their customers by themselves. They need to have the feeling that they are really understanding and looking at their clients, at the people who are coming to their concerts. So we said, okay, so unsupervised, it is probably. So how can we do that? And we make use of a technique called self-organizing maps, also called Cohonen map by the professor who came up with it. And it's an unsupervised visual clustering technique, which basically, if you have heard of it, you know this already, but it basically maps a higher dimensional space to a two-dimensional one. And the two-dimensional aspect is nice because, as you can see here, you can show it as a nice colored map outlining your customers in what's called little nodes. So immediately you have a visual way of exploring your data sets. And it tries to maintain the topology of this higher dimensional space in the two-dimensional outcome. That's basically all it wants to do. So it consists of two parts called vector quantization and vector projection. Basically says that, well, it tries to make groups out of your data. So just as standard clustering techniques such as k-means or dbScan or whatever, it makes groups out of your data set. But it also tries to make it lower dimensional compared to normal clustering techniques where at the end of your clustering run you have 5 centroids in your higher dimensional space, giving you very perhaps still hard to understand description of what the clusters are. This will also decompose this into lower dimensions. And then it becomes quite easy to go through it and to understand it and to explore it. So how does it work? Well, basically, I'm going to go through this very quickly, but it works like this. So you start by laying out a group of what's called output nodes. You can do this in a rectangular fashion or in a hexagonal pattern, any way you would like to. And you have your data set. And for every node, you initialize it with a random weight vector with the same length as the number of dimensions you have per instance. So then you go through all your instances, you calculate the Euclidean distance between the instance you have at the moment and all of these nodes. And then there is a winner, the one with the shortest distance, that's this node here, called the best matching unit. So the node that is currently closest to that particular instance wins. Now, then what happens next? That node gets updated. The weight vector of this node gets updated. And here you see the mathematical definition. What it means exactly is not so important. What is important, however, is that it gets updated by a certain learning rate. But not only this, all the neighbors of this node also get updated. So their weight vectors also get updated. So what happens is, because this one is the winner closest to this instance, it gets pulled even closer to that instance. And you do so for every instance in your data set. You run over it. You can run over it multiple times. You can run over it randomly. That's all up to the configuration of the particular algorithm. But you lay out a map. You lay out the weight vectors of every node to correspond with the instances you have. Now, at the end of this, what happens is that you see groups appearing in this map. You see regions appearing, like here in the lower right, I have the red region, and then here I have the dark blue region. And these correspond with clusters, with segments, customer segments in our case, you found in your data set. And since we know the weight vector of every node, we also know the instances that are closest to every node. So from node, we can go to instance, so we know where every instance should be placed. So me, for instance, Seppe, quite a young guy, I like the opera, I might be located here in this region, and one of you might be more in favor of electronic dance music, you go to Tel Aviv every night to party, you might be here somewhere, right? I mean, just an example, I'm not inferring anything. So you can also visualize the mean distance between these regions. That just helps you to draw separating boundaries between these regions there. So at the end, basically you get regions. Now, you can color them depending on how well they represent certain attributes in your data set. And then you can already visually compare them. So one of the things we did was we showed them these heat maps, and they went exploring and they said, well, you know, for this particular venue, the people who went there, well, we see, if we look at the percentage of unemployment, that is inversely correlated with the average education level in this case, which is what you might expect. So it's a good confirmation of what the gut feeling tells you. It's a good confirmation, well, it was a good confirmation for our partner to say, well, this can actually work, this can help us to explore this data set.
A lot of stars of David.
How so? Yeah, that's right. Yeah, that's true. So when they saw this, they said, okay, this is nice. And at the end, if you do so for every attribute in your data set, you get something like this. And then the first problem came along, and also where we had to make the first modification, and which led us to publish the first paper around this work, where this thing was breaking down. They said, well, this is all nice. We can compare how every attribute gets used in these regions. Like, for example, it is very logical that the region of men is directly inversely related to where the region of women is. And then you can take, okay, if this is the region for men, let me compare with something else what that is correlated to. Okay, fine. However, Ticketmatic said, well, we are not really interested to start here with these regions of gender and go from there. But we want to start from these regions, the concerts people went to. So here we have 5 concerts. We want to know, looking at a particular concert, what is that correlated to in their other attributes. And if you look at the concerts, well, they're laid out in a bit of a messy manner. It's hard to start from here and then look at the others and see, well, where are the correlations? They still like the idea of the heat maps, though, because that was a very visual way they could present this to their customers as well. But they wanted to drive it a bit using domain knowledge, knowing I want to go from here and explore the rest. So we came up with a prioritized way to do so, to adapt this algorithm. First of all, however, what we also did to make it easier, to make the inspection of this a little bit easier, you can apply a second-level clustering approach on these weight vectors, and then you can really show the regions immediately. And then for every region you get here in this self-organizing map, you can say, well, for this region, for example, we can tell you many people in here belong to a young age group. They're mostly students. They have a higher spending on concerts than average. So you can come up with a name. You can say, let's call this region over there, let's call them the young culture fanatics. And this really helped. Coming up with names for these regions really helped them to say, oh, now we understand the bubbles in our customer groups. These are the young people. These are the older customers. These are the rich and wealthy, and so on and so on. So they liked this idea. Now, as I said, next up, they wanted to figure out a problem to solve this issue. Like we want to prioritize on some attributes. So we came up with a very slightly modification of how the algorithm works. I'm not going to go into detail in the internals of it, but basically we assigned a weight now to every variable where our partner could indicate from their domain knowledge, I'm really interested to prioritize this attribute. I'm really interested to prioritize, for instance, on the buying behavior of my customers. So we came up with this. And then at the end, if you run the algorithm again and you indicate that you really want to start your analysis from these attributes, you see, well, regions now start forming around these attributes. It makes it much easier to then say, okay, for this first concert over here, for instance, what does that correspond to the other attributes in my self-organizing map? So that was the first thing we did there. Then the second thing, and this was actually the more challenging one, is to analyze time dynamics. So they said, well, what you're showing us now is just one static picture at one point in time, but we're also interested to know how this will evolve over time. And you can't just run this algorithm again at different points in time because the layout, it starts from a randomized weight vector. It will be completely different, and you will not be able to do a comparison there. So we came up with something different. Now, there is very little existing work around this issue and self-organizing maps to deal with time. There is one prior work which just says, well, basically the idea is here, let's keep one dimension for the data and then use the other dimension to lay out the time. So here you see weeks from the start, and it lays out the customer groups along this timeline. It's an interesting idea. We couldn't use it, however, because it means that we needed time information for, data information for every of our instances at all of these time points. Week 36, week 35, week 40, 42, and so on and so on. And we didn't have this. We just had ordered information, but not in absolute time terms. Not for every day of the week, for instance. Just this week, then maybe a month later for you, and then for someone else, maybe 2 months later. So we had to deal with this. Now, what we did is we said, well, let's again use a two-step approach. First of all, use all the data we have over the complete time range, and then apply just a sequential pattern algorithm to mine out the sequences. Now, I have to be a bit quick now, because my time is running out, I know. So what we did is first, create your groups, as before, create your clusters, and then for every customer, check through time what their movements were throughout these groups. And we did this analysis on a 3-year time span. So that's why you see the movements in the first place. You don't go from being a young culture fanatic to be an old, rich, and wealthy guy in just 1 month. So this takes a bit of time. So we did this over the time span of 3 years for the groups of interest here. And then for every customer, you see that they move from bubble to bubble, basically. Now, if you do this for your 3 million or I don't know what customers, you have a lot of arrows you need to draw. So it becomes, again, a mess. You can't see the forest for the trees. So what did we do? Well, we have all these arrows over here, all these movements. We mine out the frequent ones. That's the first approach we did. Long, frequent sequences with a good support, with a good confidence. So that's our first approach. And then the second approach is, what we could also do is we, again, apply clustering technique on these movements to kind of move the arrows together and get out the general ideas, the general movements. That's also something we did there. So 2 approaches to deal with this issue. The slide describes this in more detail, but that's the gist of it, basically. So let me show you based on this example. So this was another example where the thing we were analyzing was, we know that some people come by to buy a ticket for the first time, but then after a while they get more and more interested in what we are offering them, and they become subscribers. And these are really nice customers for us because they generate a lot of value, they generate a lot of wealth. So we would like to know what are the sequences, what are the patterns through time that cause customers to be subscribers, that cause them to be coming back. We want to know this, and we want to be able to detect this up front. So that's what we did here. So we first prioritized to say, well, all these clusters over on the top over here, they correspond with people that have a subscription. So then, as I said, we mine all the trajectories through time for all customers. You see there's a lot of them. But after then mining out the frequent ones, we saw that we find 6 discriminative sequences that cause people to end up in one of these 6 subscriber zones. Now, this was very interesting because you can look at the descriptions for every cluster and then see how people, the different ways how people evolve to the group of interest. In this case, for instance, it says, well, what we see here is that this movement corresponds to an increase in the average number of days separating the purchase of the ticket and the event itself. So meaning this basically says is they buy more upfront. So means that they're interested, because instead of just buying a ticket 1 day or 2 days before, they already buy a ticket 1 month before, because they really know they want to go to that concert, to that venue. And also, another variable which we saw there was an increase in the customer value. So you could do this analysis for all 6, in this case, patterns you find, and then understand, this is the changes in a customer that cause them to become one of these 6 groups here, that cause them to become subscribers of us. Now, this is then the other analysis by clustering on all these delta movements of the centroids. A bit less important, so I'm not going to spend as much time on this, but in the end this helped us to, this is, well, an abstract representation of what it looked like in the dashboard. Well, one problem with this was you still have to look at all the sequences one by one and understand how the variables change and so on and so on. So at the end, in the overall clustering analysis, we were able to come up with a general abstract report saying, well, you want to know what causes your customers to become subscribers? Well, the customer value goes up. If you see this happening, then a warning light should go off. And you should think, whoa, this customer, better send him a nice marketing brochure or something, because they're becoming more valuable. They will become subscribers soon. The time of purchase gets lower. They buy ticket pairs, maybe for them and their partner or for them and a friend, is increasing. And they buy more tickets per event. So it's very domain specific, of course, but you can apply this on any data set basically. But it tells the business users, hey, if you see this and this and this and this in a customer, in like 1 month or 2 months from now, they will generate more value. Those are your stores you want to keep along. So that's the message we wanted to send there. So that's what it looked like in the end. So that's it basically for the talk. Now, to come back on that one point I mentioned in the beginning saying, well, couldn't you just have predicted this with supervised machine learning? Well, definitely you could, and we did. But what we find in practice is, especially for companies that are just starting out with analytics, is that a very good step is to first present them with exploratory means, unsupervised-based means. They can play with it, they can get a feel for the data. They feel assured that what you're doing really corresponds to what they see in their data, what they feel in their minds, and so on and so on. And then afterwards, we were able to confirm them, hey, you know what, wouldn't you rather prefer that a machine gives you these sequences automatically and the idea and the description rather than having to look by yourself all the time? And then they were much more in acceptance to say, yeah, actually, can you do so? Can you do so? And then the next step came along, which was more supervised techniques there. So it's a step-by-step approach, which I just wanted to highlight in this talk for a second as well. I hope you enjoyed it. Thank you. And I'm welcome to hearing any questions or comments you might have.
Okay, so we'd like to ask, you have in several places in your talk that you present a label. How did you create that label? I mean,
that's a very good question. It's mentioned at one of the slides. Sadly, I didn't have time to go into that aspect in detail. At first, you just look at the centroids of the cluster. So basically the centroid of all these little weight vectors you have. And then you can see, well, this one is higher than average. So we can come up with a label based on these people are younger than average, for instance, or have more wealth than average, something like this. Of course, that becomes troublesome again if you're dealing with a lot of clusters. So in later stages, we implemented something which is called extraction of the salient dimension. It's pretty known research. And it does what I just described in an automatic manner. It's telling you per cluster this and this and this attribute are the ones that make this cluster special, basically. So we also implemented this in this work.
I didn't fully understand how you create the initial heat map, for example, of the concert. How does the clustering?
The construction of the initial map, you mean, right?
Yes.
Yeah. So how? That's basically just a standard self-organizing map approach. What you do is you take all the people that went to that concert, you take their attributes, and then you start running through them one by one and updating the map so that the nodes will basically organize themselves around your higher dimensional data you have there. And then, so basically, it's similar to other dimensionality reduction techniques such as PCA, for instance, that you go from a 20-dimensional representation like age and gender and wealth and this and that to a 2-dimensional topology, basically. So that is the idea behind it.
Yes, but when we talk about gender, for example, I can understand how the heat map may be created, but you said you started with a concert. I don't understand what are the... I understand you have multiple dimensions of information about the person, but how do you crunch it into a single dimension?
Well, that's basically by, so if I go back. So first of all, I should mention that I think it's for this one. So for, yeah. Yes. But in this case, the 5 concerts are just binary attributes per customer to indicate that they go to this concert, yes or no. So that's point number 1, I should mention. So here you're just taking your whole customer base, and you have 5 concerts of interest, and you just indicate if they went to this or not. And then how the map... Yeah, that's basically the idea. Yeah, that's true. Yeah, so here, well, here because it's binary, you're only interested in either the completely dark blue ones or the dark red ones. But for other attributes, such as age, for instance, there it's, of course, a continuous scale. So there the yellow also makes sense, right? So on this slide, most of these things are categorical features. That's because they had a preference to use this, but you could just as well use continuous features as well. And then the red to the blue is a much more continuous scale, of course, too, right? So, yeah.